Hey guys, this question asks, what is the major product of the following reaction sequence? Okay, so as you can see here, we have a bridgehead compound. We have this 6-membered ring with this bridge right here in the middle, and then we have an OH, a hydroxyl group. Now when you do your reactions in organic chemistry, remember we always study our reactants. We kind of look at the functional groups and say, okay, what reactions do we know of that particular functional groups? So, we have here an alcohol, and that's sort of the only really functional group on this compound. This is just an alkyl halide pretty much for the rest. It's got a ring and all that, but it's not, the rest of this molecule isn't very reactive. It's all carbon atoms and hydrogen atoms. And the only reaction really that you will have learned that reacts with that is, the radical halogenation, and that's not happening here. So for the most part, I think the magic is going to be happening around this alcohol group right there. Okay, so the first step, it says TSCl, that's Tosyl chloride, Tosyl spelled like that, and pyridine. Now what this reaction does is it turns an alcohol or an amine, but usually an alcohol, into a leaving group. Because remember, hydroxyl groups are not good leaving groups. This OH is not going to want to leave, either in a bimolecular or a unimolecular fashion. It's not going to want to just leave. It's a very stable functional group. And so in order to get rid of it, we first need to turn it into a good leaving group. And that's what the Tosyl chloride and the pyridine does. I will make a separate video in which I explain the exact mechanism through which that happens. It's not that long, but it's, Tosyl chloride's a pretty big molecule, and it's a lot to draw out here, so I won't show it in this video, but there will be another video which you can find to show exactly how Tosyl chloride turns this into the tosylate. But the tosylate looks like this. We just abbreviate it as OTS. Looks like that. And this is now a very good leaving group. You can kind of think of this as literally just this. Put a bromine there, because bromine is also a good leaving group, right? So everything you can do with this compound, you'll be able to do with this compound. Just about. I mean, OTS is actually even an even better leaving group than bromine is, in fact. So maybe, I don't know, maybe we should make this iodine. I don't know, but it's I generally think of, I imagine, instead of the OTS, I just imagine like one of the halides, the very good leaving groups, because that's what this compound is going to behave as. Okay, so now we are done with step 1. Now we do step 2. So we take this guy and say, okay, NaN3 and acetone. Now important, what does NaN3 look like? Sodium will always form the salt, right? It'll always be a plus charge, so N3 must have a negative. And this actually looks like this. I think this is a compound you should memorize. You see it very often in organic chemistry. It's actually a very unique compound in that it is a very, very good nucleophile, but it's not that strong of a base. HN3 is actually pretty acidic. So N3 minus is not a very strong conjugate base. So this guy here will be a nucleophile, but it won't be a base. It's not going to abstract a proton, but it could do something like a backside attack. And that is in fact what's going to happen here. We're going to have this this nucleophile come in and attack the back there, kicking off the OTS like that, and we'll get this hydrogen will stay on there, but the OTS will be replaced with N3. Now don't be tempted to put the N3 here, however. Remember, this is a backside attack, so it will invert the stereochemistry. So in fact, we will have this N3 with the hydrogen at the top, because the SN2, the backside attack, occurs via an inversion of configuration. Remember, it's that umbrella reaction where you have say you have CH3 iodine, and you have a nucleophile that comes in. It comes in, and everything kind of pops over, and then the nucleophile is on the opposite side of where the iodine was. So yeah, so the N3 will be on the bottom and the OTS will be on the top. And we can clearly see that that makes B the correct answer. One thing to also look out for is the word acetone. Remember, acetone looks like this. It is a polar yet aprotic solvent. And polar aprotic solvent usually indicates SN2 reactions. Other examples of that is DMF, dimethylformamide, DMSO. There's a whole bunch of others, but polar aprotic solvents indicate SN2 reactions. So when you see acetone, generally, that's sort of a hint that you're going to be doing an SN2. All right, thank you for watching.